Hello everybody and welcome to Scalar's YouTube channel. This is Mahima Hans and I'm a software engineer and a mentor. And today we're going to be talking about dynamic programming. And in this part 1 of our dynamic programming series, we're going to be covering some basics of dynamic programming, top-down and bottom-up approaches, and how we solve dynamic programming problems using both of these approaches. But before we get on with the video, make sure to check out free masterclasses by industry-leading experts only on Scalar's events page. The link is in the description. So let's get started. So before we start with dynamic programming, I want you to know that the prerequisite for dynamic programming is recursion. So make sure that you're familiar with the concepts of recursion and you understand them very well before proceeding with this video. So now let's understand what dynamic programming exactly is. So dynamic programming involves breaking down a problem into subproblem and then computing the results, the answers for that subproblem so that they can be reused to calculate the answer for the main problem. So what we do essentially is we calculate the result of subproblems and we store them somewhere so that whenever those problems occur again, we can use the results already computed and we can calculate the answer for the main problem. So it kind of optimizes the time and space complexity and it kind of stores the answers for the future purposes and avoids repetitive computations and repetitive calls. So we'll better understand dynamic programming by examples. So I'll take a quick example of Fibonacci series. So we have this sequence, Fibonacci sequence. And what essentially this means, like in the sequence, every term is the sum of the last two terms. So the first two terms are always 0 and 1. It starts with 0, second term is 1. Now the next term will be sum of 0 and 1, which is 1. The next term will be 1 plus 1, 2. The next term will be 1 plus 2, 3. Then it will be 5, then 8, then 13, and so on. So this is our Fibonacci sequence. So for any term ith term, it will be the sum of I minus 1th term plus I minus 2th term, I minus second term. So if you write the recursive code for the same, so since every term is depending on the previous and next to previous value, and the base cases for the recursion will be 0 and 1. So term at index 0 is fixed and the term at index 1 is fixed. It's always same and it's already given. And based on that, we can calculate the further terms. So let's just write the recursive code for the same. Let's say ith Fibonacci term. It will take the value I. So if I equal to 0, we'll just simply say that the answer is 0. If I equal to 1, then we will say the answer is 1. These are our base cases. In all the rest of the cases, the answer will be function of I minus 1 plus function of I minus 2. The sum of the previous two terms. Okay, and this is our Fibonacci function. Now let's say using this recursive function, you're calculating the value of the term at the 6th index. So you're calling this function for I equal to 6. So when we calculate f of 6, it will give a call, since I is not equal to 0, I is not equal to 1, it will go to this line. It will give a call to f of 5, it will give a call to f of 4, I minus 1 and I minus 2. Now for the function I equal to 5, since it's not 0 and 1, it will again give a call to f of 4 and a call to f of 3. This will again give a call to f of 3, f of 2. This will give a call to f of 2, f of 1. This will give a call to f of 1, f of 0. And then again, this will keep proceeding in this manner. So if you carefully observe here, this f of 3 was being calculated in this tree. And now to calculate it again here, we'll have to give the same calls again and again. So these calls are quite repetitive and they're unnecessary computation, which if we store somewhere, a lot of time and space can be saved. Because here also we are calculating this complete tree of f of 3 and again we are calculating it. It doesn't make sense. Similarly, f of 4, this is also being computed again and again. So to avoid these unnecessary and repetitive computations, that's where dynamic programming comes into picture. So dynamic programming will essentially avoid these unnecessary calls, and there are two conditions for dynamic programming to be implemented in any problem. So one is optimal substructure and the other is overlapping subproblems. So overlapping subproblems essentially means this f of 3 computation that we were seeing again and again. They're overlapping subproblems and they don't need to be computed again and again. So this refers to overlapping subproblems, and optimal substructure means that the answer for the main problem or a parent problem can be calculated by the optimal solutions of the other subproblems of it. So the answer for f of 4 can be calculated by the optimal answer of f of 3, and answer of f of 6 can be calculated by the optimal answer for f of 5 and f of 4. So this is what optimal substructure and overlapping subproblems means. And here in this question, since we are having all the two conditions satisfied, we can use dynamic programming to basically store the results of our subproblem somewhere. Like we'll store the result of f3 whenever we calculate it, and later reusing it when we have another call for the same value, so that computation is minimized. So let's see how dynamic programming can be applied in any problem. So there are two ways of applying dynamic programming. One is called the top-down approach or the memoization approach, and one is called the bottom-up approach or the tabulation approach. So I'll discuss both of these one by one, and we'll first discuss the top-down approach or the memoization approach. So let's discuss the top-down or the memoization approach. So what happens in the top-down approach, it's essentially a very simple optimization over our recursive approach. What we do is we maintain a DP table or an auxiliary space. Let's say we maintain a DP table of size n, and what we do is initially we populate all the values with -1. So let's say we were calculating the Fibonacci sequence of till value 4. So I'll make till the index 4, so I'll make an auxiliary DP table, and what I'll do is whenever I calculate the answer of any subproblem, I'll store it in this DP table. So whenever the next time we are faced with the same subproblem of calculating it for any particular index, it was previously calculated, we can just reuse it. So what memoization does is it essentially stores the answer of subproblems in a DP table, and whenever the subproblems recur, it just uses the already stored solutions from the table. So when we were looking at our chart, at our recursion tree, we were going to f of 5, f of 4, f of 4, f of 3, and we'll be calculating f of 4 here. So f of 3, f of 2, f of 2, f of 1, f of 1, f of 0. So here we can calculate f of 2 as f of 1 as the sum of f of 1 and f of 0. So the f of 2 will come out to be 1. Now we'll store, now our 0 and 1 we can already populate it with the base values. This will be 0. I'll update this to 0 and I'll update this to 1. Now f of 2 has been calculated, so I'll store the value 1 at index 2. This is already there. This will return 1. F of 3 will be calculated as 1 plus 1, 2, and I'll store it here. Now f of 4 needs the value of f of 3 and f of 2. So f of 2 we already calculated in the DP table and we have stored the answer here. So we can just write we can just return the answer instead of making a call again to f of 1 and f of 0. So whenever we calculated the answer, we can store it directly. So for f of 4, the answer will be 3. And when we'll again come to this f of 4, we will not compute this complete tree again. We don't need to. We will just simply take the value, computed value of f of 4 from this table, which is already stored as 3. As we just computed, we'll just put it in the TP table. And we'll take this value. The next time we come at f of 4, we don't need to recompute it. So that's how memoization works. So if you carefully observe, when we were computing it in the previous solution of recursion, we were making 2 calls at every step. We were calculating f of n minus 1 and we were calculating f of n minus 2 again and again. So even if it was already calculated, there were 2 calls at every step. So our time complexity was coming out to be O of the order of 2 to the power n. But here if you see, we are going on every index only once. If it's already computed, we're not computing it again. We just visited every index only once, and the time complexity will be optimized from O of 2 to the power n and it will go to O of n. So it's a really big optimization, and that's what dynamic programming does to recursive problems. Now we can look at the code of the memoization solution. So let's first write the recursive code that we were already looking at. So for the recursive code, it was very simple. We would just, let me just quickly create a helper function. So let's say our answer equal to helper, and we'll pass the number, the index for which we have to calculate the answer, and we'll return the answer. I'll write the helper function. So the base cases would be if n equal to 0, we can return 0 because we already know that the value for 0th index is 0. And if n equal to 1, we can return 1 because the value for the first index is 1. Now for any generic case, we were making 2 calls. We were returning the sum of the value at n minus 1th index and the Fibonacci number of n minus 2nd index. So this is the recursive code for the same. Let's just submit it. Here the constraints are really low, so even the recursive solution is working. But let's optimize it using the memoization solution we just did. So what we can do is, as I told, we'll create a DP table. So we can just say vector int DP, and for finding the nth number, we can create a DP table of n plus 1 length, and we can initialize it with minus 1. So initially at all places minus 1 will be present as we discussed, and as and when we calculate, we can replace minus 1 with the exact value that we calculated. So I'll change my helper function, I'll pass on DP. There will be essentially 2 changes in the helper function. Number 1, whenever we calculate the answer for any problem, we have to store it in our DP table so that we can reference it next time. The second change would be, before going to calculate any answer, we have to first check if it's already present in the DP table, and if it is present, we don't have to calculate it again. So here we can just check, is the answer already calculated for this particular index? So if it's calculated, the minus 1 would not be present anymore, it would have been replaced by the exact answer value. In that case, we can return the DP of n. If it's not calculated, before making these calls, like before returning the answer, we'll just store it in the DP table. So we'll store DP of n equal to helper n minus 1 plus helper n minus 2, and we'll return this answer. So check if already computed. That's one change. If not, we are computing and storing. these are the 2 steps of memoization solutions. That's the changes that our recursive code would go through. We have a small compilation error. We'll pass on DP here as well. Yeah, so this works. And it got submitted as well. So now let's discuss the bottom-up approach of dynamic programming. So bottom-up approach is an iterative approach as opposed to the top-down approach, which was a recursive approach. So bottom-up approach essentially starts from the subproblems. In the top-down approach, we were starting from the main problem and we were solving the subproblems along the way. But here, we'll sort our input from smallest to largest, and we'll first solve the subproblems iteratively in the increasing order, and then based on the solution of subproblems, we'll solve the main problem. So it's an iterative approach and it first solves the subproblems. So like in, let's take the example of the Fibonacci number only. What we were doing here was that we were starting from the main problem. Our main problem was to solve f of 6, let's say. So we were starting with f of 6. Then we were going to subproblem f of 5 and f of 4. This was further going to subproblem f of 4 and f of 3. Then further to f of 3, f of 2. So we started with the main problem and then we went ahead to the subproblems. Then we encountered the base cases and then we returned the value to the subproblems first and then eventually to the main problems. So that's how top-down approach was working. In the bottom-up, it's the exact opposite order. So we'll start with the subproblems. So if I have to calculate the Fibonacci numbers in the bottom-up approach, I'll first, I know already that the answer for 0 is 0. The answer for 1 is 1. If I have to calculate f6, I'll first calculate all the subproblems before that come before f6. Okay, so I'll calculate f of 2 first. So I'll essentially create a table here and the indexes will go till 6 since we have to calculate the 6th answer. Yeah, so 0 and 1 are already there. I'll calculate second answer, which is 1. Then I'll add these up and I'll calculate the answer at index 3, which is 2, the answer at index 4, the answer at index 5 and the answer at index 6. So instead of first calculating the answer of, like first starting to calculate the answer of main problem and then going down to find the answer of subproblems on the way, it starts with the subproblems, calculate these answers, and then at the end the main problem is solved using the answers of those subproblems. So the bottom-up approach is also called the table filling or the tabulation approach, and we'll write the code for this iterative approach now. So instead of writing it as a helper function, I'll write the code here only in our main function. I'll just write a for loop here. So here also we need a DP table of size n plus 1. So for n equal to 6, we'll need a DP table of length 7. So now I will just populate my base cases. DP of 0 equal to 0 and DP of 1 equal to 1. Now we'll go iteratively starting from the other subproblems. So it's going in order starting from 2 going till 6 or whatever n is. So here it will be from I equal to 2 to I less than equal to n, and then we will be filling the DP table, DP of I minus 1 plus DP of I minus 2. And at the end we can simply return DP of n. We can also, to avoid any segmentation errors, we can just write if n is less than equal to 1, return n, because we don't need to create this, we cannot compute values for index 2 and further in such cases. So we'll just write if n is less than equal to 1, return n. There's no need of initializing a DP table as well before that, so we'll just put this statement here and we'll run our code. Yeah, so it's accepted. We can also try to submit this. Yeah, so it works. So this is an iterative approach, and if we go for the time complexity and the space complexity of this approach, so we're going for a for loop of size n. So the time complexity here is simply O of n, and the time and the space complexity is also O of n because we're using an auxiliary array of size n. So for this approach as well, time complexity and space complexity are O of n, and the code looks quite simpler than the recursive and the memoization approaches. So now that we've understood both the top-down and the bottom-up approaches of dynamic programming, it's essential to realize what the differences between these two are, so that whenever you're solving a problem, you can figure out which one of them is the best one to use for that particular problem. So let's consider the differences between these two. The first good thing about the top-down approach is that it's very easy to implement. So like you saw, whenever we are solving a problem, the first step is figuring out a recursive relation, right? Like we figured out the recursive relation of Fibonacci series pretty fast. And then to implement the top-down approach, there's not much of code change needed, right? We just need only two changes: to store the value in the DP table and to check if it's already stored before trying to recompute a value. So it involves very less code change in the recursive solution, and so it becomes easy to implement. While in the bottom-up approach, we have to revamp the whole code. So yeah, top-down approach is easy to implement, but it's a little slower because of the overhead of recursive calls, which is not the case with the bottom-up approach, as it's an iterative approach. The other thing that comes along with the bottom-up approach, with the top-down approach, is the space overhead. So all these take a lot of space of the recursion stack, and if this case happens that the recursion tree goes too deep, it can happen that the program may crash because of a lot of space overhead. So that is one problem with the top-down approach that occurs in some cases. Now the bottom-up approach, if we notice, when we were seeing the code of both of these approaches, the bottom-up approach code seemed very simpler because it just had a for loop, as opposed to the top-down approach which had the whole recursive function and then memoizing in the table. So code is less complicated in the bottom-up approach, so it looks simpler and quite clear, quite easy to understand as well. Also, in the top-down approach, like if we have to solve a problem where we don't need to solve all the subproblems. So let's say there's a main problem which depends on certain subproblems, but all of the entries of the DP table doesn't have to be made. Like in the Fibonacci, we were populating the complete table while we were doing the bottom-up approach. We were starting from the index 0, we were going till the index n, and we were populating it on the way. But if there is a problem where all subproblems don't need to be solved, then the memoization approach or the top-down approach is a little better, because it will not populate all the entries. It will populate only those that come along the way. So if you remember, when we make the recursive calls, when we make the calls in the top-down approach or the memoization approach, we go to the subproblems. We always start with the main problems first, then we proceed to the subproblems, and we only compute those subproblems that are needed. While in the bottom-up approach, we start from the smallest subproblem, we keep solving all subproblems along the way, generally in an ascending order, and then we finally arrive to the solution of our main problem. So yeah, bottom-up approach is better when all the subproblems need to be computed. But in the cases when there's no need to compute all the subproblems, and even then we're computing it in the bottom-up approach, then it becomes a little slower, and in those cases we can prefer the top-down approach. Also, in these cases where all of them don't need to be computed, in these cases bottom-up approach does unnecessary table entries, while top-down approach doesn't do any such thing. Another thing about bottom-up approach is the speed. Now bottom-up approach is a simple for loop, and we are storing the entries in a table while going through the input set. So whenever we want to refer to the answer of a subproblem, we just look at the answer stored in the table. So it's just an operation of accessing the entry in the table. But in the top-down approach, we have to go through a couple of return statements and a couple of recursive calls before we can find this answer. So it's a small difference, but it does matter in big problems. So yeah, the speed of accessing the sub-problem answers is better in the bottom-up approach. So these were the differences in top-down and bottom-up approach, and these will help you choose the right approach for your problem. So continuing with our discussion of the Fibonacci series problem that we discussed recently. So we discussed two optimized approaches for the problem. After recursion, we discussed our top-down approach, memoization approach, and our bottom-up approach, which was our tabulation approach. So in the top-down approach, the time complexity was O of n, the space complexity was O of n as well. The same thing was true for the bottom-up approach, where the time complexity and the space complexity were both O of n. But even further space optimization is possible in this problem. Let's understand how. So if you look at the relation, the recursive relation for a Fibonacci number or a term of this sequence, so f of I comes out to be the sum of f of I minus 1 plus f of I minus 2. So the answer for any current term is essentially depending on previous term and the next to previous term. All the other terms don't affect the current answer. So if I am calculating the answer for the term at index 2, let's say, it will depend on index 0 and index 1. The answer will be 1. Okay, if we move to index 3, the answer will depend on index 1 and index 2. The answer will be 2. If we move to 4, the answer will depend on index 1 and index 2. It will be 3. So if the answer is depending on only these two previous terms, maybe instead of storing all the entries in the DP table, we can just store these two entries which are useful in two variables and keep updating these variables for the future entries. I'll show you on this example, but instead of maintaining this whole DP table where we're starting from 0 and we're populating values in the DP table, when only the previous two entries are useful, instead of making this table, we'll just maintain two variables, previous one and previous two. Let's see how. So let's say this is our table, this is our sequence, and we are calculating the answer for, let's say, index 8. So initially we have, this is our previous one variable. So this is just the previous variable and this is next to previous, which is previous 2. These are the two variables. Okay, we are going by the top down, we are going by the bottom up approach and we are calculating the answer iteratively. So when we are calculating answer of 2, we refer previous 1, previous 2 and fill up the answer as 1, the sum of these. Now when we reach index 3, we need these two. So what we do after calculating index 2, we make this as previous 1 and this as previous 2. So we'll first assign the value stored in previous 1 to previous 2. And then we'll update our previous 1 to be the answer that we just calculated. So we'll update previous 2 to be this number first, and then we'll update previous 1 to be this number. So since we got this, now our previous 1 and previous 2 pointers are this, so next term will be calculated as 2. Then again previous 1 will be moved here after computation and previous 2 will be moved here. And then we'll be referring to these two variables and computing the next answer, which will be 3. So on and so forth, all these answers will be computed, and that's what we realize, that we only need two variables instead of the whole array. So let's write the code for this and see how it works. Let's write the fresh piece of code. Okay. So our previous to previous will be the 0th index, and our previous 1 just previous to the second index will be the index 1 and the value there is 1. So these two things are there. Then we'll start for computing it from index 2. So from index 2 till index n, the current answer will be the sum of previous one and then previous 2. Now we will update our previous 2 to become previous 1 and previous 1 to become current answer. So keep in mind, these statements have to be written in this order only. We can't update previous 1 first and previous 2 later, because we have to update previous 2 as previous 1 first. If we update previous 1 first with the current answer, we'll lose what value was there in previous 1. So if we update it, previous 1 will be populated with answer, the current answer. But what we want is first populate previous 2 with previous 1. So whatever was previous 1 will become previous 2 next to previous, and then previous 1 will become answer. So keep in mind to maintain the order of these statements. And then we can just return previous 1. Because whenever we'll be coming on the last variable, whenever we will be calculating it for, let's say, n equal to 0, 1, 2, 3, 4. Okay, let's say we had to calculate for n equal to 4. Now when we calculate the current answer, after that previous 1 will become this and previous 2 will become this. So this will be the answer. The answer will be stored in previous 1 all the time. It will be last to our next term. So since we don't have to calculate the next term, the answer is already stored in our previous 1 variable and we can return that. Let's run this code. Okay, there is a small error. We have to name it as previous 1. Yeah, this works. We can submit this. Awesome. So it has a good runtime. The time complexity is optimized, but the space complexity is significantly optimized, and we're doing it in space complexity of O of 1 because we're just using 2 variables. So space complexity is significantly reduced in this solution, and this is significantly optimal over the previous solutions that we discussed. So I hope you were able to understand what dynamic programming is and how we can solve problems using top-down and bottom-up approaches, and what are the differences between these two approaches. In the next part of dynamic programming series, we'll be solving a few problems related to dynamic programming from LeetCode. If you got value out of this video, make sure to like it. If you have any comments, feel free to mention them in the comments section and we'll be happy to answer all of your doubts. Make sure to subscribe to Scalar's YouTube channel for more such informative content. See you in the next video.